Okay, so last class we started talking about vectors. We learned an approximate approach to adding vectors, which was our graphical method with the protractor ruler. You guys did one of those for me. Oh, I have those. I'll pass those back in a little bit. They were all fine. But we're really not going to do the protractor ruler anymore because, of course, it's just an approximate way to get the exact answer. And to do that, we need to learn how to add vectors by components. So you sort of looked at this in your homework last night. If you have any random vector, you can think of it as the sum of 1,000 other vectors. It could be any vectors like this, plus over here, plus this way. So long as we were adding them head to tail, the resultant would still be tail of the first to head of the last. Now, of course, there'd be no point in doing that, but we can think of each vector as a sum of its components, which would be perpendicular to the x and y axis, because we know how to do math with right triangles. So it's really helpful to have components that are parallel to each of the axes. All right, next slide. So for example, let's say you want vector A plus vector. All right, vector A is red. Vector A is sort of like this. You can draw this if you want. Sort of. And then vector B, it's a little bit longer in the directions over there. So adding it head to tail, that's what I would end up with. And my result would be like this. Green. Okay, so I've got my answer. I know it's the green vector. All right, imagine I erased A and B. I'm just going to leave behind that green one. Sort of. And this time, instead of dealing with A, I'm going to look at the components of A. AX and AY. And I'm going to look at the components of B, so BX, to the best of my drawing ability, and BY. And we typically combine the x's together and combine the y's together. So AX was to the left, like so. BX was to the right. So I'm still adding these head to tail. So starting here, going to the right over a little bit. AY was up, but I'm not quite to my resultant yet. And then BY was up just a little bit more. So you can see, it's just another way of adding up vector A and B to get the same exact result. It's going to be the same answer. It's just that I'm actually now dealing with 4 vectors, the x and y of A and the x and y of B, in order to get the resultant. What you notice is nice about the resultant is that you have this little triangle you made. And that's sort of our goal, is to make right triangles, because we can do the math for right triangles. Okay, so that bottom of the page. All right, in the figure, which of the ways indicated for combining the x and y components of vector A are proper to determine that vector? So the components, they would still be added like vectors. AX plus AY should equal A. It doesn't really matter where I put AX and AY, but they do need to add up head to tail to equal vector A. So does it look like A does that? All right, let's look at A. So AX is this way. AY is straight down. So if I add them head to tail, if I imagine moving that vector over here, does that equal the picture of A? No. That would be like down and to the left. That would be my result. All right, what about B? No, same thing. I'm still looking down and to the left. How about C? Yeah. Yes, of course C is correct. AX plus AY does equal A there. How about D? Does it matter if it's AX plus AY or AY plus AX? No, order doesn't matter. D is fine. Let's add up to make A. Again, tail of the first to head of the last. Resultant should be vector A. What about E? No, E is like the negative of A. E is going the opposite direction it should be going in. And what about F? Yeah, even though they didn't draw it to make a triangle, F would be true. AX plus AY would equal A for F. Okay. Okay, so of course it's useful to work with the x and y components because they will of course make right angles. And vectors that fall on one of the axes, like this one right here, 5 meters north. I mean, what would you say AX is? Yeah, it would be nothing. Because the x components, how far left or right do you go? Well, you don't. It's just straight up. So you can have components that equal 0. And we like it when components equal 0. That makes it a lot easier. Okay, so here's a problem we did today graphically, but we're going to do it by components today. Plus. All right, we're going to add A and B. And we have an approximation from yesterday, but today we're going to do it with components. So first it says solve for the components. And I always recommend just a little sketch just to kind of see what our answer should look like. Just a sketch. So, and we already did this anyway, but if A is 10 meters at 15 degrees, okay, that's roughly over here. And B is 5 meters at 130. Okay, let's kind of back like that. And that was my resultant. So I've already got a guess. It should make sense that my resultant's between 0 and 90 degrees. Looks like, according to my little sketch, looks like 45. But use your sketch to make sure your answer makes sense, because sometimes I get just completely wrong answers. And you could have easily told me that was between 0 and 90 degrees, and yet I'll get an answer that's way over here that doesn't make sense to your sketch at all. All right, now we're going to sketch them separately and do the components like you're doing for homework. So here's A. So AX is to the right and AY is up. And I don't necessarily like you to get in the habit of thinking, well, AX always means I need to do cosine, or AY is always sine, because you could have just as easily drawn your triangle by drawing AY first. I mean, that would have been the same, it would give me the same resultant, same thing. Doesn't matter the order. So just sketch it out however you want to sketch it out. Look at your sketch and decide what is the appropriate trig function to solve for that side. So that's your hypotenuse. AX would definitely be your adjacent side, knowing that that's 15. So that is what function? Cosine. So you need to rearrange, but you know that cosine of 15 equals adjacent over hypotenuse. So pretty much you just need to do cosine of 15 and multiply by 10. Of course, making sure our calculator is in what mode? degree mode. And I need some help on that. 9.66? All right. And then if one was cosine, the other one would be sine. Got an answer? 2.55? 59. Okay, so we've solved for our components. Now, one more thing we need to do is just look at the magnitude, look at the direction. This is right, this is up. Do I need to add any negative signs to that? No. So, we're good to go. All right, now let's look at B. So B was over here. And all of this was 130. But this is the way I drew my triangle. So yeah, I need to think about what angle makes sense in my triangle. I know all of this is 130, but I drew my triangle this way, so I really need to worry about that 50 degrees in order to do my trig. Again, it did not matter if you drew a BY first and then BX. You'd just be using a different angle. You'd be using 40 degrees in that case. So we're doing, and our hypotenuse is, of course, the 5 meters. Okay, so we're doing sine of 50 times 5 for y, cosine for x. Anyone got y?
3.83.
And x? All right, I'm very good with the negative. Please always check, are any of your components down or left? If so, you want to make those negative. Okay, so now what do? Add them all together. And keep the x's and y's separate still. So Rx, my resultant x vector, my resultant x component, is the sum of all the x's. 9.66 and minus 3.21. Oh, yes. I don't know what I was thinking. All right, and then same for y's. Add them up. 2.59, 3.83, they're both positive. So of course, that's going up. No. Oh, and I can already tell they're really, really close. That probably was a 45-degree angle, or very, very close to it. Okay, and what I've really figured out here, I've added up the x components, I've added up the y components. Back to my original picture, even though this was originally A and this was originally B, I now know these sides of the triangle. Rx here and Ry here. So ignoring the blue and the red, and I'll redraw that. No. I figured out what Rx is at 6. Ry, 6.42 meters. So I still neither answer. Okay, Pythagorean Theorem. Do your 6.45 squared plus 6.42 squared, square root that. And we get something. What is it? Okay. Sorry, let's put our unit in there, meters at. So don't stop, you're still not done. You've got the magnitude, you know the hypotenuse now is 9.1, but I need to tell somebody else how to be able to draw this vector. Good, this is where you want to do your inverse tan. You want to find that angle, and it would be 44.9 degrees. I think yesterday when we did the graphical method, I had 9 at maybe 43. It was okay. Obviously not exact, but it was decent. And that's it. That is how you would get your exact answer using the components method to add vectors. A few words of caution on dealing with your angles. If, for example, you had solved for a resultant vector that was down here, and maybe you had sketched out Rx and Ry, and in which case Rx and Ry would have both been negative, and you do your inverse tan and you solve for your angle and you get the angle to be 20 degrees. Yeah, that is not the answer that you should record, because if you tell somebody to draw a vector at 20 degrees, they're not going to draw it down here. So just bear in mind, you know, what coordinate you're in, or what quadrant you're in, and like you said, yeah, add 180 to that. So whatever this answer is, it would be, you know, something at 200.
And then that
right, and you're always squaring it with Pythagorean Theorem, so you'd never have negative magnitude. But our direction tells us, the angle tells us our direction. All right. Okay, 43 real. Okay, so 43 looks like it's the vector sum of vector d1 plus vector d2. So it says in the figure, what are the signs of the x components of d1 and d2? So the x component of d1, and you're simply asking, you know, is it left or is it right? d1, the x component would be to the right, so positive or negative? Positive. All right, what about d2? As far as x goes, it is still positive. All right, how about y? What's the y component of d1? Positive, it would have been up. What about the y component of d2? That's negative because it is down. d2 is down and to the right. So positive x but negative y. What are the signs of the x and y components for the sum of d1 plus d2, which you kind of have to imagine is drawn in there? Yeah, tail of the first to head of the last. That resultant would be up and to the right, so positive and positive. All right, now just a little bit on something called unit vector notation. The unit vectors, these are vectors that all have a magnitude of 1, so you can pretty much multiply them onto any vector you want and not change the magnitude of that other vector, but they all have a certain direction. So unit vector I just means a vector of 1, whatever, along the x direction, positive x direction. So I goes with x, j goes with y, and then if you imagined z like coming out of the board, that would be k. So sometimes you'll see vector A written as, you know, like our answer just was a second ago, 9 meters at 43 degrees. Or sometimes it's already simplified for you into the components, which is, it's really nicer when it's done that for you because you don't have to figure out the components. It's going to tell you the components right off the bat. So to write your x component, we would just put the magnitude of x and then just stick the letter I with our little vector notation to indicate that that was in the x direction. And that's it. So if you were given the vector E which had components 3 meters east, 4 meters south, and 2 meters upward, which we would use that for the direction. Oh, another way of writing that is simply 3 for my magnitude. How would I indicate east? Just the eye. Well, hold on. 4 meters south. Okay, so here's my 4. 4J. But it does have to be negative, because I want to indicate south and not north. So you would have just negative 4J. The J just means I'm talking about the Y direction. Negative, now you know it means down. All right, and 2 meters upward, K. So that's it. Oh, it's there the whole time. Okay. Oh, wrong way. Okay. Last slide. Find the sum of vectors A, B, and they're in the XY plane given below. So find the sum. So we're adding vectors. You know you need to do this graphically. But they've already given you the components. How easy is that? So they've already given you the components. Just combine the x's together and combine the y's together and go from there. No? Oh, my bad. So our x, the total x component would be given by what? Yeah, 2 plus 2. And that was positive. I don't really need the I, but I've already got it indicated by the x. And the total y component would be 2 minus 4. Yeah. So I've got my overall x, overall y components, but how do I use those to answer the question of find the sum? What'd you do? The Pythagorean Theorem? Okay, perfect. You've got your components. You might want to think about it as a little sketch here. 4i, okay, that's x, positive x direction. From there, adding these head to tail, I've got negative 2j. So that is my answer. So you did Pythagorean Theorem, and what did you say it was? Give me the decimal version. And these are meters. All right, here's a good one to practice. How do I get an angle for that? Yeah, and don't, sorry, I should not have written that negative. You can tell the direction by the way it's drawn. Thank you. So my answer, so the angle in the triangle I drew is 26.7 degrees, but the answer angle would be what? How will we get it?
All the way around.
Yeah. If I want to tell somebody how to draw this vector, I do not want to tell them to draw it at 26.7 degrees. You've got to realize that's all the way around. What I would do is just realize the full circle is 360, and you're 26.7 short of that. You could use your compass directions. You could just say 26.7 degrees south. That would be good. Sometimes it's not consistent with whatever our problem is doing. All right. Whole bunch of threes? There you go. All right, that is all of chapter 3. Congratulations, you did it in a day and a half.